Hello and welcome back. Today we're going to look at logarithmic functions. Before we look at the logarithmic function, I'd like to first review exponentials. So if we have the function 4 to the x, and we wanted to plot these points, well, 4 to the negative 1 is 1/4, 4 to the 0 is 1, 4 to the 1/2, which is the square root of 4, would be 2, 4 to the 1 is 4, and 4 squared is 16. Now if we're going to sketch that here, this function would be increasing, and we definitely know it's 1 to 1. So if I wanted to sketch the inverse of this function, all I have to do is switch the values for x and y. So this would be 1/4 -1, 1 0, 2 1/2, 4 1, and 16 2. When I plot those points, the function will look like this. Remember that when we have inverse functions, it's like a mirror. They're reflected on the line y equals x. Now this function, the inverse, is a logarithm. So the logarithm is the inverse of the exponential function. So if we're going to write this as an equation, the inverse of this exponential function would be log base 4 of x. Well, looking at some characteristics, we can see that the domain of the logarithm function is 0 to infinity. We can see that the range, though, is -infinity to infinity. So it flip-flopped from the exponential function 4 to the x. Now instead of having a horizontal asymptote, this is going to have a vertical asymptote at x equals 0. And it's going to have an X-intercept at 1 0. So the logarithms is looking at this comparison of powers of 10. And Napier really was the one that put this on the map, publishing his discovery in 1614. And then he worked with Henry Briggs to create what we see in logarithm in its modern form. And years ago, before we had calculators, we would have tables of logarithms in the back of our textbooks. So let's look at some of the properties here. We're going to evaluate logarithms. When we evaluate them, there's two main things I want to make sure we cover. The common logarithm, that's when we have a base 10. And you could say, we're looking at powers of 10, and yes, that is a very common number. So we're going to use base 10 with a common log. And oftentimes, you won't see log base 10. You'll just see the word log. And that implies that it has a base 10. Now, in exponential functions, in the last section, we covered Euler's number. And when we have base e, we also said it was a naturally occurring compounding continuously number. So this is its inverse will be a natural logarithm function. And so instead of saying log base e, we use ln, the natural log. And remember x, that power is going to be greater than 0. All right, let's evaluate some of these using the definitions. So we're going to plug in, we want to solve here. So this is going to be our power right here. So we're trying to figure out what this equals. And I'm going to put 32. So when you have an exponential function, that base for the inverse becomes a small number here. So oftentimes, what I like to do is set this equal to y and rewrite it into exponential function. So this will be 2 to the y. I use a little Nike swoosh. So 2 to the y equals 32. Now we know that 32 is going to be a power of 2, right? So that's going to be 2, 4, 8, 16, 32, that's the fifth. So since those are equal, we know that y equals 5. So looking back, when you see this 32, it's asking, what is the exponent? 2 raised to what value will give you 32? And here we equal 5. Now let's look at log of 3, log base 3 of 1. So we're going to rewrite this using the little swoosh. So 3 to the y equals 1. So what do we need to raise 3 to get to 1? And that would be 0. So whenever we have log base 3 of 1, then that is going to simplify to 0, because 3 to the 0 gives you 1. Now let's look over here. So this is log base 4 of 2, using that little Nike swoosh. So we have 4 to the y equals 2. We're saying 4 to what power gives you 2? Well, we can do a couple things. You can probably figure it out really quickly, but 2 squared equals 4. And so we know 2y equals 1 because those bases are the same, so it's y to 1/2. And that makes sense because the square root of 4 gives us 2. Now remember, this is a common log because we don't see the base. And so we're trying to simplify log of 1 over 100. So when I rewrite it into exponential form, that's 10 to the y equals 1 over 100. And 1 over 100 is just 10 to the negative 2. So this will simplify into negative 2. We're looking for the exponent. So 10 raised to what power gives us 1 over 100? And that must have been negative 2. The properties of logarithms, you probably start to see a few of them, are going to also apply to the natural log. So whenever we have a is greater than 0 and x is greater than 0, if we have a log base a of 1, that's going to equal 0 because a to the 0 equals 1 and e to the 0 equals 1. When you have log base a of a, that equals 1 because a to the 1 equals 1. Just like you would have natural log of a equals 1 because e to the 1 equals 1. Now if we have log base a of a to the x, that's going to equal x because a raised to the log base a of x also equals x. And same thing with natural log. The natural log of e to the x is going to simplify to equal x because e to the natural log of x equals x. Remember, these are opposite or inverse operations. Now the last one is when we have two logs equal to each other. And in these cases, you do not need to rewrite the expressions or equations into exponential form. So for here, we actually know that the bases are the same for those natural logs, so x must equal y. And that's still the case with natural logs too. If natural log equals the natural log of y, then x must equal y. All right, so let's simplify these. Some of these are going to be very fast, so you don't need to rewrite them. But if you do not know them, you can always set them equal to y and rewrite them into exponential form. But we know 4 raised to the 0 power would give us 1. Because 4 is greater than 0, and then 4 raised to the 0 is 1. Now for this one, this may not be easy to identify right away. So I'll rewrite this into exponential form. So square root of 7 equals, so let's do this one more time. I'm going to write over here, square root of 7 raised to the y equals 7. So I'm going to rewrite this as 7 to the 1/2 times y equals 7 to the 1. So we know that 1/2 y equals 1, so y must equal 2. And that makes sense because if you're squaring 7, then you'll get back to 7. Now let's go to the next one. Natural log of 1 over e. Now this is, you can do a couple things, but I'm going to rewrite it, okay, so that we can have this equal to y. Remember, this is going to be e to the y equals 1 over e, because natural log is log base e. Now, 1 over e is just e to the -1, so y must equal -1. Another way we could have written it, I'll use different color here, is writing this as natural log of e to the -1. And we know that natural log and e cancel each other out and you get -1. So over here we have e raised to the natural log of 5. So we know that these operations are going to cancel each other out, and we'll be left with 5. Just as over here, we have natural log of e, that's going to cancel each other out, and we'll be left with 2 times 1, or just 2. Now natural log of 1 over 3, that's going to be 1/3 natural log of 1. Well, we know natural log of 1 is an identity. So natural log of 1 is just going to equal 0. So 1/3 times 0 is just 0. So this will equal 0. Now let's go to solve some of these. To solve these logarithms, we need to make sure that both sides have a common base, just like we did with exponents. So this is log base 3, log base 3. So since they're equal, well, we know that x equals 12. When we have logarithms, we want to make sure that this number is true, because there is a restriction for the x. X always has to be greater than 0. So when I plug that in, yes, you can see that that's still going to be a positive number. Now we have the common logs, so we know that 2x plus 1 equals x. So in subtracting x from both sides and subtracting 1, we know x equals -1. Now when we plug in -1, we get -2 plus 1. So that's going to be log of -1. And remember, that cannot work. We cannot have a -1 as a power. So this will be no solution. Or you can write empty set. Now let's look at log base 4. Well, we can set these equal to each other. So x squared equals 16. When we take the square root, you'll get x equals plus or minus 4. And when we plug them in, we still get a positive number, 16 minus 6. So they both will work. Okay, so we're not saying that x can't be negative. We're saying what you plug in needs to make sure that we have that power as positive. Now we have a natural log here, so we have x squared minus x would equal 6. We can bring the x over here to the left side. So we get x minus 3, x plus 2. So x would equal 3 and x would equal negative 2. When we plug them in, this will be natural log of 9 minus 3, so that checks out. We still have a positive number there. And then natural log of 4 plus 2, so that works out too. So even though we have a negative here, they still work out and we still get natural log of 6. Now let's go back to the graphs. So we know that the natural log, or the logarithm I should say in general, is going to have a domain of 0 to infinity, a range of negative infinity to infinity, an x-intercept of 1, 0, it's increasing, it's 1 to 1, right? Its inverse is the exponential function. The y-axis is the vertical asymptote. It's also continuous, right? And it is a reflection on that line y equals x. So let's look at some transformations. When we have log base 4 of negative x, so it's really almost like that. This is going to be a reflection on the y-axis. So the function is going to be going down here. So instead of 1, 0, it's going to be 0, or sorry, negative 1, 0. So this will be the x-intercept. This is decreasing. The domain is now negative infinity to 0. The range is still all real numbers. The vertical asymptote is still x equals 0. There is no y-intercept, and the x-intercept is now negative 1, 0. When we look at negative log base 4 of x, that's going to reflect on the x-axis. So we're still going to have the same x-intercept, but now it's going to be decreasing. So it's decreasing here. The domain is still 0 to infinity. The range is still negative infinity to infinity. These didn't change. The vertical asymptote did not change, and neither did the intercepts. Now let's look at a translation. This is going to make it shift 1 unit to the left. So that means the vertical asymptote will also shift, and the x-intercept will also shift. So this function is still increasing. The domain is now negative 1 to infinity. The range didn't change. This vertical asymptote did change to x equals negative 1. There is a y-intercept now because the x-intercept is now 0, 0. For this next one, the logarithmic function is going to go up by 1. So everything's getting shifted up 1. So we can see right here it's still increasing and nothing changed with the domain or the range. Now the only thing that's going to change is going to be the x-intercept. And we're going to have to use a calculator to solve that. So let's see, we have log, if we plug in 0, well, let's see, that's just going to be, to set this equal to 0, excuse me, so this is going to be log of x equals negative 1, and so we'll have x equals 10 It's just, oh, it's common log. So we'll have 10 to negative 1. So x equals 1/10. So 1/10 and 0. So just very small. All right, let's consider some functions with multiple translations. So for this one, I actually just had one. It just shifted down. So this one's going to go down 4. It's still going to have, I'm going to write this over here, the domain is still going to be 0 to infinity. The range will still be negative infinity to infinity. The vertical asymptote didn't change. There's still no y-intercept. And then if we want to find the x-intercept, we could solve that too. Probably don't need a calculator for this. So I'm going to set this equal to 0. So log base 3 of x minus 4 equals 0. I'm going to isolate the log and then rewrite it into exponential form. So 3 to the 4th equals x. So that's just going to be 81. So my x-intercept will be 0, 81. And obviously it'll be very far to the right. Now let's have multiple transformations. There's a couple things here. We're going to shift to the right 5. And then we're going to stretch and reflect. So reflect on the x-axis and stretch by 2. So there's 3 things going on here. Okay, so initially, it was shifted to the right here. Initially the function would have gone through, but now we're going to reflect it, so it's going down, or it's decreasing. And let me move this. So make sure that's 5. So we had the vertical asymptote is shifting to x equals 5. We know that the domain and the range doesn't change. But the domain is going to go from 5 to positive infinity. That reflection, again, is going to make it be decreasing, but it's still going to go through. It's pretty steep over here, so this is just a sketch. And you can see that that y-intercept is also going to move. So if we wanted to double check, well, you can set this equal to 0. And the negative 2 will go away. And let's just erase it here. Divide both sides by negative 2, and you'll have 10 to the 0 equals x minus 5. So that's just 1. And you can see that the x-intercept is going to be 6. And there's no y-intercept here because of that asymptote. All right, let's look at the next one. For this problem, we know that's going to shift left 2 units. It's going to be reflected on the y, and then it's going to go down 4 units. So when I shift it to the left 2, that changes the horizontal asymptote, or so the vertical asymptote. And then when we reflect it, it's now going to be at positive 2. So we know that this graph is reflected and then it's going down. So if it goes down 4 units, it's going to be very steep here, like that. So we know that this function is going to be, the domain will be negative infinity to 2. The range is still negative infinity, all real numbers. The vertical asymptote shifted to x equals 2. We know that it's decreasing. It will have both an x-intercept and a y-intercept. So to find the x-intercept, we set this equal to 0. And this will be a weird number, but we could say it's going to be e to the 4th equals negative x plus 2. So this will be e to the 4th equals, we'll subtract 9 minus 2. And then I'm going to multiply by negative 1. So ends up being x equals 2 minus e to the 4th. So that's going to be our x-intercept. And our y-intercept is when we plug in 0. So that's just going to be natural log of 2 minus 4. So 0, natural log of 2 minus 4 is our y-intercept, and our x-intercept is 2 minus e to the 4th, 0. And remember, we're making sure we stick with the order. So we're looking at the factor, whatever is next to the x. Then we look at the reflections. And then we're going to consider the stretches. And then last but not least, the vertical translations. For our final example, we're going to look at applications of logarithmic functions. So when we covered exponential functions, we talked about compounding continuously. So this function will actually give us the time if we want to see how long it will take for an amount to increase k times the principal amount after t years with a rate of 6%. So we want to see how long it will take, what's the time, to first double the value. So when we plug in k equals 2, we'll have natural log of 2 over the rate, which is 0.06. And that's going to take about 11 and a half years for that investment to double. Now let's consider, when will this investment triple? So again, k is our multiplier. So we're going to say, what is the time? So natural log of 3 over the rate of 0.06, and that will be about 18.31 years. Well, I hope this lesson was helpful, and I'll see you all in class.